All right, in this video, we are going to look at vector operations both graphically and algebraically. So vector operations are super useful because they will tell us what we can expect, how we can expect different vectors to relate to each other. So for instance, if you have a vector like vector 1 and another vector is like acting upon that, you can add them together, and we'll talk about how to do that. But on a graph, you just put them end to end, and then you get this resultant vector, which will give you the new magnitude and direction when vector 1 and vector 2 act together. So it's kind of confusing. This one maybe will make a little bit more sense. We're back to this picture with the plane, and the propeller is headed in this direction at this magnitude, and the wind is going in a much different direction at a smaller magnitude. The question will be, what path will the plane actually travel based on the wind? So then to figure this problem out, you might be able to visualize that. But you take the propeller's vector and you add it to the wind's vector, and to add them you go end to end, and then you connect them, and this will give you the new magnitude of what the airplane will actually travel and the direction. So let's look at how that works. We have 3 examples on your note sheet, and we're going to look at each example both graphically and algebraically. Okay, so here we have vectors u and v in component form. And for this first one, we're just looking to add u and v together. So if you have a graph, what you do is, I'm going to start with vector u, and that one's already graphed right here. And then I am going to add vector v. But when you add them, you have to go end to end. So I start with u, and then I'm going to take the end of v and put it on the, put the tail of v on the head of u, whatever, just end to end. And this represents u, this represents v, and then u plus v, you start where you started and you end where you end. So this is called the resultant vector. So this green one is u plus v. So if we have something going in the direction and magnitude of u, but then some other force is taking it in the magnitude and direction of v, the green is where it's actually going to end up. And these are it's parallelograms essentially, right? Or a diagonal of a parallelogram, because v, like the v that I drew, should be parallel to this v and the same length. And then this is like the diagonal, like the parallelogram. If I drew u would be here. That's, I guess, what I'm talking about. Now, it's hard for me to draw really well with this. So here's what it would look like a little bit neater and a little bit more in proportion. So u plus v is this green resultant vector of u plus v. It doesn't matter what order you add. So if I had started with v and added u, check that out. The resultant vector is the exact same thing. Okay? So this is what you would do, like if it asked you to add the vectors on a graph. Algebraically, it's even more straightforward, or it's easier for me to do because I have trouble drawing really accurately on a graph. But u plus v, it's really intuitive. You add the horizontal components and you add the vertical components. If I'm adding u and v, I'm going to take -2 plus 5, so that'll be my new horizontal, and my vertical will be 3 plus 7. So then what I have is 3 in the horizontal and 10 in the vertical. Boom, that's my new vector, the resultant vector. And check this out. If I eyeball this on my grid, 3, 10, 3 in the horizontal, 10 in the vertical, yeah, that's where that resultant vector would be. All right, let's look at the next example. I have u and v again. This time I'm just looking for 3u. Well, that means 3 times u, 3 of u. So I already have 1 here. So to add another one, and by the way, I'm adding because 3u is the same as u plus u plus u, right? So I have my first u, I draw my next one, and I draw my next one, and that's it. This is 3u. There's no other resultant vector to, like, there's nothing else to draw in because I'm already end to end, and here's where I started, and here's where I finished. So this is my resultant vector, okay? Mine aren't perfectly drawn to scale, but here's a better representation of that. This is 3u. And if I were graphing that, I would label it like this too to show that, hey, this is 3u. Okay. As far as algebra goes, I could take this and add it 3 times, or I could take this and, by the way, v is irrelevant to us right now, so I could take 3 times the horizontal component, and then 3 times the vertical component, and I would get my resultant vector of -6 and then 9. And if I go back over to my graph, -6 in the horizontal direction and 9, that's where I end up. So these should give you the same thing. This is just on a graph, obviously, and this is the component form. We're going to look at one more. Okay. So the last one, -2u plus v. Okay, so on a graph, think about what -u might be. Like if you had to imagine what -u is. -u is just going to completely reverse the direction. It's going to just reverse that direction. So -u is going to look like that. So -2u, I need 2 of those, and it's going to look like that. So this part is -2u. And then if I want to add v to that, remember you have to go end to end. So -2u, and now I'm adding v, so I'm looking in this direction at that magnitude. It's going to be about like that. And then, so this is v, and I only have one of them that I'm adding. So the resultant vector, here's where I started, here's where I finished. So the resultant vector is this one. So this is -2u plus v. Algebraically, by the way, wait, before I do the algebra, here is a nicer picture of that that's drawn to scale. Okay, u goes here, so -2u, it goes in the opposite direction, and I have 2 of them, and then v, and then the resultant vector from where I started to where I finished. Okay, so algebraically, what I'm going to do is I have -2 of the u's, so I'm going to take -2. I'm going to write it this way. So I'm going to take -2 of vector u plus vector v. So then this distributes. So -2u is actually +4 in the horizontal and -6 in the vertical. Plus v does not change. And then 4 plus 5, that's going to give me 9 in the horizontal, and -6 plus 7 is going to give me 1 in the vertical. So my new vector is 9, 1. So 9 in the horizontal direction and 1 in the vertical direction. All right, that ends the basics of vectors. We will start looking at applications and go from there.